Get your favorite dishes delivered home.
Okay, hello everyone, good morning. Please type in your name. Okay, so last class we were discussing about GOC and that too resonance. We have discussed how to compare the stability of resonating structure. Okay. Now, few applications of this resonance we'll see. Okay, and there we have the calculation of bond order and then aromaticity. Actually, there are 3-4 application of resonance we have. So just you write down here. Application of resonance. Okay. So the first application we have the comparison and calculation of bond order. Calculation of bond order. Second one we have aromaticity. Little bit aromaticity I have discussed in the last class and I told you we'll discuss in today's next class. Okay. So today we'll see some examples of aromatic compounds and anti-aromatic compounds. Those examples you have to keep in mind. Okay. Then we have, you already know this plus R plus or minus R, or we also call it as plus M and minus M group. We have mesomeric effect that comes under resonance only. Stability of intermediates, we have discussed stability of carbocations with respect to I effect. Okay, stability of intermediates. So here also it is the same thing we have, right? Like plus I is electron releasing group, stabilize carbocation and destabilize carbanion. So here also we have plus M group, electron releasing group, stabilize carbocation, destabilize carbanion. Okay, like that we have here also. Okay, and then last one we have heat of combustion and heat of hydrogenation. That is, let it be, that is not required here. So first thing that we are going to discuss today is the bond order. Okay, so how to calculate bond order in the resonating structures, right? So first point to write down, we'll just see this bond order thing and this aromaticity. These two we'll discuss. Okay, and then some of you have asked me to discuss that bond, what we say, molecular orbital theory, VBT, and all some concepts of chemical bonding. Okay, that also we'll discuss today itself. So these two, then concepts of little bit concepts of chemical bonding we'll discuss. Okay, and then if we get time, we'll discuss tautomers also, tautomers and percentage enol content. Okay, we'll just do the revision of that because that is also an that is nothing but information. If you know all those cases, you can do the question. Okay, if the question comes directly from there, but if you do not know, you cannot do that question. Okay, it is there's okay. So that's the point. We'll discuss percentage in all content. Tautomers will discuss a little bit what all cases we have, condition and different cases. and then these two plus some concepts of chemical bonding. That's why this class is for 4 hours. Okay, so we'll try to finish all this. Okay, so first of all, you write down the first thing we have bond order. See, bond order, we have discussed this in chemical bonding. You must have done this, and we calculate bond order of various molecule or ions. Right, the most common we have this one, O2 2 minus, O2 minus, O2 and O2 plus. This question has asked many times in the exam. Okay, the bond order of this. Anyway, so here we are not going to discuss this. The point is what? We calculate this bond order according to what? MOT, that is molecular orbital theory. Right? And the formula of bond order we have discussed here is what? Number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2, right? This is the formula we have. Correct. So this formula we'll discuss when we do the MOT, right? Today only we'll discuss chemical bonding, also we'll do this here. But here, since we are talking about application of resonance, so the molecule in which resonance is applicable, resonance is there. How do we calculate the bond order of that? Like suppose if I give you formic acid or formate ion, and if I ask you to calculate the bond order of CO bond in formate ion, then what is the answer? That is what we are going to discuss today. So first of all, you see the bond order is what? It is the effective number of bond between the two atoms present in a molecule. Okay, the definition of this you see, it is the effective number of bond present between the two atoms in a molecule. Okay, effective number of bonds present between the two atoms in a molecule. Why we are calling it as effective? Since we are talking about resonance. Suppose if I draw here benzene, right? Benzene is this, and the resonating structure of benzene, the other structure we can draw is this one, right? If it is 1 and 2, this is 1 and 2. So what will be the bond order of this, the C1 and C2 carbon in benzene molecule? You cannot say 1 or 2, because why this thing is there? Because resonance is possible into this. So that's why we are calling it as effective number of bonds. Okay, since resonance is possible here, right? And usually when the molecules, in any molecules, when resonance is not possible, we usually say it is the number of bonds present between the two atoms in a molecule, right? We also have this information that bond order is directly proportional to what? Bond energy. Bond energy or bond strength also we call it as, right? More will be the bond order, more will be the bond strength, and inversely proportional to bond length, right? So in resonating molecules, if you know the bond order, you can also compare the bond energy of that particular bond, right? Bond strength of that particular bond. Okay, now how many of you, or you must have this information, that since we're talking about effective number of bonds or bonds between the two atoms, but bond order of any molecule can be fractional also. This information you have already, right? That the value of bond order can be fractional also. Integer fine, but it may have some fractional value also, and this we have discussed again in molecular orbital theory. We have seen this, that bond order can be any fractional value also, right? There are two values, different types of value of this bond order possible. The first one is integer, right? And this is very easily like we know this, you can understand it easily because it's the number of bonds, so it can be an integer, right? But it can be fractional also, right? And that we have seen in MOT. See, this fractional value of bond order is possible when resonance is possible, in case of resonance, right? So in case of resonance only, the fractional value of bond order will be possible, otherwise it won't be possible, right? Integer value will be possible when there is no resonance. So we have discussed about this bond order and we know the fractional value is also possible, but there we haven't discussed about what? Why this fractional value is possible. So the fractional value is possible because of resonance, because of delocalization of electrons, pi electrons, right? Now, you see how to calculate this bond order. Now, the main thing is the calculation of bond order, okay? So, see, the calculation of bond order is possible when we have equal contributors. Okay, for unequal contributors, since the stability will be different, okay, so bond order of the molecule of the two atoms, two bonds between the or two atoms present in the molecule, the bond order calculation is difficult over there when we have unequal contributors, right? So that we'll discuss later on. The first case we are taking here, that calculation of bond order when we have equal contributing structures. Equal contributing structures, or we can also write it as equal contributors. Okay. So here you see the first example. I'll try to make you understand with one example here. Suppose the example I am taking, that is formate ion. Formate ion is H, C double bond O, O minus. And the other structure of this will be HC, single bond O minus, double bond O. Right? So now, here you see, if I ask you, suppose this is first atom and this is second atom, and we have to calculate the bond order of we can say carbon oxygen bond. See, in this molecule, again, like I took the example of benzene ring. Similarly, you cannot say the bond order of CO bond is 1 or 2 here. Understood? Why you cannot say? Because you see, in 1, 2, this carbon oxygen bond, if you are considering, here we have double bond, here we have single bond. So you cannot say 1 or 2, right? Why this thing is possible? Because of resonance, right? So in this case, the formula of bond order, the calculation of bond order, we do by this formula. And this formula you write down, bond order, okay, is equals to the summation of total bonds in all resonating structures divided by summation of number of RS, means total resonating structure. Simply you can write down total number of resonating structure. Have you seen this formula? Yes or no? Yes, have you seen this formula? Tell me fast. You haven't done this bond order calculation in resonating structures. Okay, anyways. So you see, basically, if you know the bond order, you know the stability also. That's why we are doing this. So you see here, the formula is the total number of bonds in all RS. And what is this bond? Like suppose we are calculating the bond order of CO bond, right? So we'll take the total number of bonds between carbon and oxygen in all RS, right? So you can take 1, 2, and 3, right? Or you can also take, suppose you're considering these two carbon and oxygen, so two bond here and one bond here, right? So what we can write, two here present and one here we have. So 2 plus 1, total number of bonds between the carbon and oxygen, 1 and 2, is 2 in this structure, 1 in this structure, divided by the total number of RS. Total number of RS is what? 1 and 1, 2. So 3 by 2, that is 1.5. The bond order is 1.5. Bond order is 1.5. Okay, anyways. So this is the bond order of carbon and oxygen bond. Okay. Another example you see. Second one. Just I'm leaving some space here. Okay, we'll use this space later on. I'll just give you one more trick here. So just you see the second example. Suppose I'll give you this carbonate ion. Okay, that is C double bond O, O minus, O minus, and you can easily draw the three different structures of this. Okay, these are the three different structures we have. Now suppose we have to find out the bond order of this carbon and oxygen bond. 1 and 2, 1 and 2, 1 and 2. So bond order according to this formula will be what? See, Ritvik, we have to calculate the bond order of carbon and oxygen, right? So any of these bond you can take, either this carbon oxygen or this carbon oxygen. Any one of these we can take. So I'm taking this one, 1 and 2, 1 and 2. So number of carbon oxygen bond present in this structure is 2, and number of carbon oxygen bond present in this structure is 1. So 2 plus 1 divided by the total number of resonating structure, 2. So 2 plus 1 by 2, 1.5. Right? Similarly, here you see bond order will be what? 2, 3, and 4. So 4 divided by 3. So 4 by 3 is the bond order. Okay. Another one you see. Double bond, positive. You draw the resonating structure of this. Okay. And tell me the bond order of this bond, 1 and 2. Any one carbon-carbon bond. Bond order of carbon-carbon bond. Tell me. How many resonating structure possible here? 3. Right. So bond order will be what? 2, 3 and 4. So again it is 2 plus 1 divided by 3 resonating structure 3. So 4 by 3. Right. How it is 0, Vaishnavi? See, this is the conjugated system. Sigma pi and vacant p orbital. Positive charge means what? We have vacant p orbital. When this bond comes over here, right, here we'll have the positive charge. Okay, so 4 by 3 is the what we say bond order here. This example, fourth one, R S double bond O minus double bond O. Tell me the bond order of sulfur oxygen bond. What is the answer? Five by three. 5 by 3 is the answer. We'll get 5 we'll get total bond will be what? 2 plus 2 plus 1. So bond order will be 2 plus 2 plus 1 divided by 3 resonating structure possible, and this minus charge will be on this oxygen, this oxygen, this oxygen. 3 different resonating structure. So that will be 5 by 3. Now for this one, what is the answer? Bond order you have to calculate for carbon and carbon. So this one you don't do, because again you can draw the resonating structure, calculate the number of resonating structure and the number of bond between the carbon atoms. Any two carbon atoms you can take. Why any two? Because we are considering all example you see that we have discussed so far, and this all we are discussing for equal contributors. Okay, this formula is applicable only for equal contributors. Okay, if the equal contributors are not there, then we do not calculate then we cannot calculate the exact bond order. Okay, we'll take then some approximation there, but this formula is applicable only for equal contributors. You see all these examples, the molecule has equal stability and equal contributors, right? These all are equal contributing structure. Okay, so here you see in this molecule, again you have to draw the resonating structure, calculate the number of RS, take any two carbon atom and count the number of bonds present between the carbon atoms. That you can do already, but I won't ask you to do this because this is again time taking. I'll give you one more formula here, one more trick that we use to solve this kind of question. Okay, and the trick is what? You see, bond order we calculate in case of equal contributing structures. Okay. The another formula of bond order, and it is just a trick we have, it is not the formula. It is the number of sigma plus pi bonds present in the molecule divided by the number of sigma bond. Sigma plus pi by sigma you have to calculate, right? And one important thing that you have to keep in mind here, that the sigma and pi bonds we only calculate for the atoms which is involved in resonance, right? Like you see this example, this carbon hydrogen bond is not involved in resonance, so this sigma bond we don't count, right? We always count the number of sigma and pi bonds for those atoms which are involved in resonance. Is it clear? So you write down this condition properly here. Number of sigma and pi bonds is, we'll calculate only for those atoms which are involved in resonance. Okay, wait, Sanjana, I'll explain. Just give me a minute. How will you know if any compound in an equal contributors? Okay. Okay, so some of you have doubt in equal contributors. Actually, you see, um, okay, I'll just come back onto this formula. Okay, just I'll discuss this equal contributing thing once again. Okay, see, suppose if I take the example of this um, okay, I'll take this example. See, here we have negative charge, double bond, and double bond. Negative charge or lone pair, you can say. Now, when you draw the resonating structure of this, there are 5 different resonating structure possible. You see, first of all, okay. Now, in this, you see the resonating structure you'll draw like this. This lone pair comes over here, and this pi electron goes here, right? So here we have the double bond. Here we have negative charge, and here we have the double bond. Another one is what? This negative charge comes over here, and this pi electron goes here. Right, so here we have double bond as it is. Double bond will have here then, and here we have the negative charge. Again, this negative charge goes here, this pi electron goes here. So here we have negative charge, double bond, this comes over here, and this goes here. So double bond, and negative charge. Is any other structure possible in this? We don't have any other structure possible. Yes. If this bond comes over, this pi electron comes over here, this will come here, and then we'll get the first structure only. So we are talking about this example, right? Now in all this structure, you see, one by one, the negative charge is present on all carbon atoms. Suppose this is the first carbon. Suppose this is 1, 2, 3, 4, and 5. So here the negative charge on first carbon, here the negative charge on third carbon, negative charge on fifth carbon, negative charge on second carbon, and then the negative charge on fourth carbon, right? And we know all these resonating structure will contributes into the hybrid structure, real hybrid, right? They contributes their property to real hybrid, right? Now the point is, when this negative charge is present on all the atoms present in the ring, it means that this negative charge is distributed uniformly or equally over the 5 carbon atoms. Fine. So when equal distribution is there, then the resonating structure is said to be what? Equal contributors. Right? So you can conclude 2-3 things into this. How do we understand equal contributors are there? The charge, whatever it is, positive or negative, this charge must be delocalized uniformly over the entire molecule, right? Or equally over the each atom present into the molecule, right? Then only it is equal contributors. Now, when you draw the resonating hybrid of this, so since the negative charge is present over the on all the carbon atoms, so it is equally delocalized. So we'll write down this ring here, means the pi bond is delocalized equally. And if you write down the charge on each carbon atom, so one negative charge is distributed among 5 carbon atoms. So each carbon atom will have charge -1/5, -1/5, -1/5, -1/5, and -1/5. Right? So this is what the real hybrid of this structure. Actual structure is this. All these are resonating structure. So when the charge distribution is equally over the each atom present in the ring, then the molecule is said to be what? Then the resonating structure is said to be equal contributors. Is it clear? Fine. So whenever you have to find out whether the equal contributors or not, just you draw the resonating structure and see whether all these charges are present on each of the carbon atom or not. Now, if you see all those examples that we have done, there the charge is present on each of the molecule. Right here also you see this is present in oxygen, oxygen and oxygen. This is the alkyl group, we don't consider this, right? Or hydrogen, if it is there, we don't consider this. This example we have discussed just now. Another thing what you can conclude here, since the distribution of charge is uniform, right, and it is equally distributed over the carbon atom, so these kind of molecule is said to be aromatic compounds. Aromatic compounds. When the distribution of charge is equal, then the compound is aromatic, right? Now, like I told you in the last class, for aromatic compounds, Huckel's rule will follow, right? Huckel's rule. And in Huckel's rule, we'll find out what? The number of pi electrons. If it is equal to 4n plus 2 pi, then it is said to be aromatic. That is what we have discussed last class. So you see here, any of this molecule you see, a number of pi electrons you calculate. 2 plus 2, 4, and we calculate this lone pair also into this, right? So 2 plus 2, 4 plus 2, 6 pi electron we have here. So for n is equals to 1, Huckel's rule is followed, and that's why the compound is aromatic. Fine. So actually this Huckel's rule is given. See, actual thing for aromaticity is this only. Planar molecule and uniform distribution of charge. When the charge is uniformly distributed, that is only possible by resonance, right? By resonance because pi electron we are considering. And resonance is only possible when the molecule is planar. That's why you see when we discuss today the aromaticity, there we have condition. The condition is what? Huckel's rule must be followed and the molecule must be planar. This kind of condition we have. So those things is necessary for resonance to take place. So the actual thing or the basic thing for aromaticity is what? Uniform distribution of charge or equal distribution of charge in planar molecule, right? So from this only we get aromaticity, right? And when we observe, we observe this what? Whenever we have equal distribution of charge, the molecule is highly stable, right? And with this only observation, we have given this number of pi electrons formula, Huckel's rule. But since it is just a observation, just an observation, so it is not true for all kind of compounds. Like I have given you one example in the last class. There we have 4n plus 2 pi electron, but the molecule is not aromatic since it is what? It is non-planar. If you remember, I have given you this formula, this compound. This one I have given you last class, and you see the number of pi electrons follows Huckel's rule, right? But this is not an aromatic compound because the molecule is not planar. Now you see if the molecule is not planar, then obviously this resonance is not possible. The charge or the pi electron will not be distributed equally over the entire molecule, and that's why it is not aromatic. Is it clear? Okay. So aromatic compounds, if you have to find out, you can also do this. Try to draw the resonating structure, try to analyze the structure, and whether this pi electron is equally distributed or not. If it is equally distributed, then the possibility of aromaticity is there. Since, and then you have to check the molecule is planar or not. Anyways, so all these molecules you see, coming back to the topic we are discussing now, all these molecules you see here, in all these molecules, you see oxygen, this negative charge is distributed equally over the oxygen atom, minus half here. Here it is minus 2 by 3, minus 2 by 3, minus 2 by 3. Here you see this positive charge on all the carbon atom. Here, then here, and then here. All these are equal contributors. I hope it is clear now. What is equal contributors? Now you see, like I said, that these kind of structure, this one you see. Now in this, if I have to find out the bond order of these two, what will be the answer? See a bond order of, suppose, okay, I'll take this one. Let me write this 4 and 5 only, equal to 4 and 5. The bond order you have to find out. So what we'll do according to this formula, 2 plus 2, 4, 5, 6 and 7. So it will write 2 plus 2 plus 1 plus 1 plus 1 divided by the number of resonating structure is 5 divided by 5. So answer will be 7 by 5. Right? So when you draw this resonating structure, you can calculate the bond order, and whatever the bond order of 4 and 5 carbon we have, that will be the bond order of all of the carbon atom if you check. How? Why? Because the equal resonance is there, equal contributors are there, right? 1 and 5 also you will calculate, you will see the same values. You see 1, 2, 3, 5 and 7, 7 by 5. For all other carbon atoms, the bond order will be same, and that's why we are using this formula for only equal contributors. Now the point is, it is very difficult in the exam to draw all these resonating structure and find out. Not much difficult, but it is time taking, right? So what we do, we don't, you know, we do not use this way to find out the bond order. But what we'll do, you see the last one, I have given you this formula. You have to find out simply this one, sigma plus pi by sigma. Okay? Only one thing you take care here, that sigma and pi is the number of excuse me, number of sigma and pi bonds present between the atoms which takes part in resonance. Okay, like I said, this sigma bond you don't consider because it is not taking part in resonance. Only we consider what? Sigma bond present here and pi bond present here. So according to this formula, if you calculate the bond order of this particular molecule, you see how many sigma bond? One here and one here. Two sigma bond and one pi bond divided by sigma 2. 3 by 2. Same value we are getting. Right? For this one, you see, if you have to calculate bond order from this formula, 1 sigma bond here, 2, 3. Right? So 3 sigma and 1 pi divided by number of sigma 3, so 4 by 3. Here you see 1, 2, 3, again 3 sigma and 1 pi, so 4 by 3. 3 sigma and 1 pi by 3, so it is 4 by 3. Yes, so with this formula you can calculate directly. You don't have to draw the resonating structure. Okay, here you see number of sigma and pi. All these carbon atom is involved in resonance. Number of pi bond, obviously 2. Number of sigma bond, 1, 2, 3, 4, 5. 5 sigma divided by 5. That's why it is 7 by 5. This one you calculate bond order. Number of sigma bond is what? 1, 2 and 3. This we do not consider because it is not taking part in resonance. So 1, 2 and 3. 3 sigma, 2 pi divided by 3. So it is 5 by 3. Is it clear? Just a second. Okay, so now I'll give you some question on the same concept. You have to find out the bond order quickly. Okay, let's write down the question here. Cl double bond O, double bond O, double bond O, and O minus. Phosphorus double bond O, O minus, and O minus. Benzene ring, bond order of benzene ring. CH3 double bond O, O minus. NH2 CN double bond NH2 plus. The bond order of carbon and nitrogen here. Carbon, nitrogen. Yes, first one is 7 by 4, correct. Second one, five by 4, correct. Third one, 3 by 2, right? Fourth one, 3 by 2, right? Fifth one, oh sorry, made a mistake here. This is H. This one is H, not nitrogen. This is CH. Hydrogen. The last one is also 3 by 2. Okay. So like this, you can calculate the bond order, okay, of all these molecules. So just let me write down. Bond order will be 4 plus 3 by 4, 7 by 4. Bond order is again 4 plus 1 by 4, that is 5 by 4. For this, we have 6 sigma 3 pi divided by 6, 9 by 6, which is 3 by 2. For this, we have 2 sigma 1 pi by 2, 3 by 2. And for this, we have 1 plus 1, 2 sigma 1 pi by 2, 3 by 2. Okay, so like this we can calculate the bond order, and then we can compare the stability of the two compounds also. If more will be the bond order, more will be the bond strength or bond energy, and hence the stability, right? Okay, now if you observe all these bond order, this is nothing but the average value we are calculating, right? Total electrons or total bonds divided by number of structure possible. Total bonds, number of structure possible. So this is nothing but the average distribution pi electron, right? And why we are taking average here, kind of average only you can understand, because the distribution of electron is equal distribution is there. Why? Because equal resonance is there, equal contributors is there, right? That's why it is average thing. But when the equal contributors are not there, the distribution is not equal, then we cannot take average also, right? So in case of unequal contributing structure, you see the next type. In case of unequal contributing structure, in case of unequal contributing structures, we cannot use that formula, okay, because that is nothing but the average, okay. And in this case, we cannot calculate the exact bond order, cannot calculate the exact bond order, okay. We can speculate here that what should be the bond order, and which, like, we can say that the bond order should be in this range, okay, and closer to this value, okay. We cannot say the exact uh, value here, right? Why? Because the contributors are not equal, so we cannot take average of those electrons, right? Some of the resonating structure will be what? Some of the resonating structure will be uh, like behaves as major contributors, and some of the minor contributors. And we know the more stable resonating structures are major contributors, and less stable is minor contributors. But in the previous case, all resonating structures are equally stable, right? So they contributes equally. That's why we are calculating bond over there. Now you see this example, if I take the first example in this case, it is CH2 minus C double bond O and H. If I draw the resonating structure of this one, the structure will, will be CH2 double bond CO minus and H. Right. Now if I ask you here, what is the bond order of carbon oxygen bond in this molecule. In this molecule, it will be 2. C double bond O, 2. In this molecule, the bond order of carbon oxygen bond is what? It is 1. So what we can say, the bond order of carbon and oxygen bond in this structure, like when you draw the hybrid structure of this, the real structure, will lie in this range, greater than 2, 1 and less than 2. Is it clear? Greater than 1 but less than 2. So we can say this, that the bond order will lie in this range. Okay, exact value we cannot say. Yes. Now, if I ask you the bond order will be closer to 1 or 2, what will be your answer? The bond order will be closer to 1 or 2. What is your answer? Closer to 1. Why it is 1? Because second structure is more stable. Yes. The point is, in this case, the bond order will, find out the like approximate value of bond order according to the relative stability of resonating structure. And that we have already done. Which rule we are applying here to find out the stability? See, number of pi bonds are same. Charge separation is also same, right? Then we use what? Negative charge on more electronegative element is more stable, right? That rule will apply on more electronegative atom, right? So according to that, this structure, which is B and A, the stability of B is more than to that of A. This means what? This is the major contributor. Major contributor, and this one is the minor contributor. And this will contribute more into the real structure, resonance hybrid. That's why the bond order of the real hybrid will be closer to 1. So for real hybrid RH, bond order will be closer to 1. Right? So the value of bond order will be somewhere between 1 to 1.5, that we can say. Understood this? So like this also, you can compare two different molecules, the bond order of two different molecules. They'll give you question like this only, so that you are able to compare if you know this. Okay. And then according to the bond order, we can find out the stability of the molecule. Second one, you see, one last example. If I have these molecule, chlorine, and then chlorine. This is alpha and this is beta. The bond, what is the bond order of alpha? What is the relation of bond order of alpha and bond order of beta? Which one is more, which one is less? Alpha is less. Why? because in this resonance is possible, right? So when resonance is possible, and here we do not have resonance, alpha is less. Tell me what happened. Bond order between two carbons. Bond order between this carbon and chlorine bond. CCl, this alpha, this alpha, this alpha, this beta here. Carbon and chlorine. What is the answer? See, Puvik, when you draw the resonating structure, right? Here we have partial double bond characteristics, no? This we have, and this lone pair comes over here, and this pi electron goes here. So this bond will have partial double bond characteristics. So this bond order will be between 1 and 2. And since here there is no resonance possible, the bond order is 1 only here. So bond order of alpha is more than this. That's why it is stable. More bond order, more stability. Yes, right, Saundarya. Fine. So like this, you see, we can compare the bond order of two different molecules, and then according to that, stability also. Correct? If we have equal contributors, exact value of bond order we can calculate. For unequal, we'll just do the speculation or approximation to find out the bond order. Right? If you have to compare the stability of two resonating structure, then we have 8 rules that we have discussed last class. According to that, we'll find out the stability of resonating structures. Okay, so this is it for in this one. Now the next thing we are starting is aromaticity. Aromaticity. Okay. Now, what are the conditions for aromatic compounds we have? So, write down conditions for aromaticity. The first condition we have, the cyclic molecule must be there, and it has planar structure. Cyclic molecule and planar structure. Or we can also say must have means conjugated system, we can say indirectly, must have available p or available p orbital for delocalization. For delocalization, the delocalization of electron is important for aromaticity, and for that we must have vacant orbital, p orbital. This is the one condition. Second one is Huckel's rule. that the molecule must has 4n plus 2 pi electrons, right? Where n is equals to 0, 1, 2 and so on, any number, any integral number. Third one must have conjugated system, which is nothing but for resonance it is possible. Must have conjugated system. Okay, these are the conditions we have for aromaticity. And like I said, these are the basic rule, but there are some compounds in which they does not follow these rules, but they are aromatic, right? So those compounds you have to memorize. Okay, you have to keep in mind. I'll give you enough example into this. Okay, first of all, if I take the example, some aromatic compounds you see. This one we have already discussed this just now, and negative charge here. Negative charge and lone pair will count in pi electrons. While calculating this pi electron, will count lone pair also into this. Okay, that's you must take care of. So how many pi electrons we have here? 2, 4 and 6. So 6 pi electrons, and 6 pi electrons follows Huckel's rule when n is equals to 1. So that's why this compound is aromatic. Simple one, aromatic. If you consider benzene ring is also an aromatic compound because it has 6 pi electrons. 6 pi electrons, aromatic, right? How many pi electrons we have into this positive charge? How many pi electrons? Tell me the number of pi electrons. 2 pi electron. Positive charge will not count, only one pi bond. So we have 2 pi electrons. And 2 pi electrons, again you see, for n is equals to 0 it is possible, right? So this is also an aromatic compound. Okay. If I take the example of naphthalene, naphthalene is this, last class also we have discussed. How many pi electrons we have here? Ten pi electrons, right? 5 pi bonds, 10 pi electrons. Again, for n is equals to 2, it is possible. So aromatic, right? Aromatic. One more example. All these examples are important. Okay. Okay. Double bond here, and we have double bond here. Positive charge here. How many pi electrons we have here? 6 pi electrons. So 6 pi electrons. So it is also aromatic. All these are aromatic compounds. See, this compound, the name of this compound is propylium ion. Okay, the name is also important, you must remember. Propylium ion. Okay, 1, 2, 3, 4, 5, 6, 7. 7 carbon atoms are present in propylium ion. All these are, you see, all these are aromatic compounds. If there are simple compounds where there is no exceptions or planar molecule is there, just you calculate number of pi bonds, right? And number of pi bonds, if it follows Huckel's rule, then it is aromatic compounds. Okay, and all these atoms you see, none of the carbon atom is sp3 hybridized. Okay, none of the carbon atom is sp3 hybridized. Okay, none of the carbon atoms is sp3 hybridized, so that is also one necessary, because you see, if the carbon atom is suppose if I write down this example, you see how you can relate this. Suppose if I give you this molecule and this one, since pi sigma pi conjugation is there, so you can draw the resonating structure, and that structure will be double bond here, positive charge here, and negative charge here, right? And the resonance hybrid of this molecule is this. Okay, we have from this carbon to this carbon. You see, in this structure, the electron or pi electron is not distributed over the entire molecule. There is no uniform distribution. Why uniform excuse me? Why uniform distribution is not there? Because these two carbon atoms are what? sp3 hybridized. And we know sp3 hybridized carbon atom does not take part in resonance, right? So that's why this molecule, if you have any sp3 hybridized carbon atom present in the molecule, directly you can say the molecule is non-aromatic. Okay, because the uh, resonance or complete delocalization is not possible. Okay, that's the thing. So this is not an aromatic compound. Okay, and you don't have to count number of pi bonds and all in this. Okay, you don't have to even consider whether the molecule is planar or not. Just you see carbon atoms sp3 hybridized, non-aromatic. Here you see all the carbon atoms, none of the carbon atom is sp3 hybridized. Okay, that is one point you keep in mind. Now, one note you write down here. Write down, in polycyclic system, in polycyclic system, still now the example that we have done, that is very straightforward. Based on those concepts, Huckel's and all, you can do that. Now some exceptions and some different kinds of compound we'll see. In polycyclic system means what? When the system contains more than two ring. When more than two ring is present, Huckel rule. Now there are slight modification into this. Huckel's rule is applicable only for peripheral pi electron. And this is just an observation. Okay, there is no logic behind this. Okay, like I said, still studies going on, research is going on in aromaticity. So things are not explained now, not properly explained now. Okay, so this is just an observation that when we have polycyclic system, we'll take this or that, like this we have. Okay, so here if I take one example of, so this you must keep in mind, this is when we have more than two ring. Now you see this molecule. Okay, double bond, double bond, double bond. We have here alternate double bond. Then it is here. This is the ring, right? Now in this compound, if you calculate the number of pi electrons, 1, 2, 3, 4, 5, 6, 7, 8, right? So for 8, so we have what? If you calculate all these pi electrons, then the number of pi electrons will be 16, right? But this molecule, according to 16, you see it follows 4n pi rule, 4n pi electrons, which is for anti-aromatic, AA. If the molecule contains 4n pi electron, it is anti-aromatic. Okay, so according to this, you see it is anti-aromatic in nature. Okay, but the thing here it is what, that we can draw the resonating structure of this. When this pi electron goes here, this pi electron comes here, and this pi electron will come here. So the resonating structure, when you draw, you will get this. We have double bond here, double bond here, and here. And all these bonds will be as it is. We have double bond here. Okay. Now the rule is what? In polycyclic system, when we have more than two ring, right? In that case, we apply this Huckel's rule only for peripheral, peripheral what? Peripheral pi electron, right? So this electron here also you see, this is not the peripheral pi electrons because it is present between two molecules. Or peripheral means what? You have to start like this. You have to go like this. All these edge you have to follow, and along this edge, whatever pi electrons you are getting, that you have to count. Right, this one from here to here. So 2, 4, 5, 6, 7. Right, 7 into 2, 14, which is true for this. In this molecule, if you see resonating structure, this pi electron, which is in between, this pi electron is non-peripheral. Is non-peripheral. So out of 8 pi electrons, 8 pi bond, 1 pi bond you don't have to consider. We consider only 1, 2, 3, 4, 5, 6, 7. Right? So in this case, the number of pi electrons, this non-peripheral, we will not consider for Huckel's rule. So number of pi electrons for Huckel's rule into this will be 7 into 2, 14 pi electrons, and then for n is equals to 3, it follows Huckel's rule, and hence the compound is aromatic. Is it clear? Okay. So now, like one rule that I have given you, that is Fry's rule, number of benzenoid form, right? So if you calculate the number of benzenoid form here, it will be 1, 2, and 3. We have 3 benzenoid form. And here we have only 1 and 2 benzenoid form. So according to that Fry's rule, this should be more stable. But like I said in the last class, that when aromaticity is there, that will overrule the all other concepts of stability that we have, right? So since this compound is aromatic, that's why this is more stable than this one. Is it clear? Next one, write down. There is a compound general name called aniline. Sorry, aniline. ANNULENE. Aniline. These are the actually cyclic compound which contains alternate pi bonds. Okay, like you see this example. This, right? This is, we have alternate pi bond present. Just a second, something. 1, 2, 3. Double bond here. And then we have double bond here. So this is aniline. General name is aniline. But we write this as what? The name of this compound is 14 aniline. This 14, this number represents the number of carbon atom present. Okay. Okay. This 14 represents the number of carbon atom present. So 1, 2, 3, 4, 5, 6, 7. 7 pi bonds, 14 pi electrons, compound is aromatic. Another one you see. One, two. How many pi electrons? What is the name of this compound? What should we write the name of this compound? What is the name of these two compounds? Number of carbon atom is 3, 3, 6, 8, 10, 12. So it is 12 aniline. Similarly, this one is 3, 3, 6, 8, 10, 13, 16. This is 16 aniline, general name. Number of pi electrons here, 1, 2, 3, 4, 5, 6. So it has 12 pi electrons. right? So this one is anti-aromatic, 4 and pi. This one has 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have again 16 pi electrons anti-aromatic. No, this one is anti-aromatic. This compound you see, this one I have discussed last class. One, two, three. Okay, this is 10 aniline. 10 aniline. This is non-planar structure. Like I said, the repulsion between here and here, right? These 2 points. This structure is non-planar and hence it is not aromatic. Okay, non-planar, hence it is not aromatic. Okay, so these are a few examples of anilines we have that you must keep in mind. Now we'll see another examples of whether the molecule is aromatic or not. I'll just write down the structures here. You have to tell me the number of pi electrons and then the behavior, aromaticity and aromatic or anti-aromatic or non-aromatic, anyone. Non-aromatic, if it is any sp3 hybridized carbon will be there. Okay, you see a few examples. This is boron. You must take care that resonance also you have to consider. Resonance is possible or not. This is nitrogen. Tell me all these first. Anti-aromatic, just you write down AA. AA for anti-aromatic. Aromatic is A and non-aromatic is Na. That's it. Anti-aromatic, aromatic and non-aromatic. First one has 4 pi electron, correct. Because boron has electron deficient, it has vacant p orbital but no lone pair on it. So 4 pi electron, it is anti-aromatic. What about this one? 6 pi electron, aromatic. Third one, anti-aromatic, because it has 4 pi electron. So it is anti-aromatic. What about this? Fourth one. Fourth one, Kushal is saying aromatic. Vaishnavi, non-aromatic. Non-aromatic. Purvik, aromatic. You see, this carbon atom is sp3 hybridized, Kushal and Purvik. So it is non-aromatic. Right? Sp3 hybridized, non-aromatic. What about this one? Fifth one. How many pi electrons in fifth one? How many pi electrons? See, actually, these two pi bonds, we have 4 electron, and this lone pair is involved in resonance. But this lone pair is not involved in resonance. Not in resonance. Okay, so this also you should know. So 2, 4, 6. It has 6 pi electrons. So it is aromatic. 8 pi electrons you can consider. But since this pi electron is perpendicular to this plane, so this is not involved in resonance. This is involved in resonance, this pi electron. Right, so this is aromatic compound. Understood? Next. Sixth one is aromatic. How many pi electrons? 6, 1. How many pi electrons also you tell me? Number of pi electrons also you tell me. Only 6 pi. You see, 1, 2, 3, 4. This lone pair is also in resonance. 1, 2, 3, 4, 5. 5 pi electrons. So we have 10 pi electrons present here. And the compound is aromatic. The lone pair is involved, that you must know. Right? This lone pair is involved in resonance. What about this? How many pi electrons? Seventh one. Seventh one has 2 pi electrons. So it is aromatic for n is equals to 0. Right? What about this one? How many pi electrons? 6 pi electrons. Both negative charge will consider here. So it is also aromatic. This one, Ninth one. Ninth one, this one. See, oxygen has two lone pair. Out of two lone pair, one lone pair each on each oxygen is involved in resonance. 2, 4, 6, it has 6 pi electron. The compound is aromatic. Okay, so this lone pair will not be there in the question. Okay, you should know this. Oxygen bonded with 2 bond, so 2 lone pair. Nitrogen bonded with 3 bond, so 1 lone pair. This information you should have. Right, so it is also aromatic. What about this one? How many pi electrons? Two electrons are there. But you see this carbon atom is what? This carbon atom is sp3 hybridized. So this will not involve in resonance. So it is non-aromatic. Okay. This one, we have done this. It is aromatic, 2 pi electrons. This one, 4 pi electrons, it is anti-aromatic. Yes, 2 pi electrons in 11th. Ninth one, this one, right? See, Vaishnavi, in this ninth one, oxygen has two lone pair of electrons, each oxygen, right? But both this lone pair is not involved in resonance. One lone pair is in the plane of this ring, and other lone pair is in the perpendicular plane. So out of the two lone pair present on each oxygen, only one lone pair is involved in resonance. So one lone pair here, one pi bond here, so two electron, and one lone pair here. So 2, 4, 6 pi electrons it has. Right? So it is not like all lone pairs you have to consider. You should know this, that out of the given number of lone pair, or the number of lone pair which is present, out of that how many lone pair is involved in resonance. Only that electron you have to consider while you are calculating the number of pi electrons. Okay? Or if you are trying to figure it out that whether Huckel's rule is applicable or not. Okay? So this you should know, like some examples of nitrogen. You see this lone pair also, we have a lone pair here, right? If I put positive charge here now, suppose in this molecule, if I put positive charge here, like this one you see. Positive charge, double bond, and one lone pair. What about this? Tell me. It has 4 pi electrons, correct? 2 plus 2, 4 pi electron. Because this lone pair is in the perpendicular plane. This is not involved in resonance, this lone pair, right? So 2 plus 2, 4 pi electron. Now it is anti-aromatic. But when I put negative charge here, then 2 plus 2 plus 2, for 6 electron we have, then it becomes aromatic. Clear? If you put negative charge here, then 6 pi electrons, it becomes aromatic. Understood? Okay. Now some more example you see. Tell me these four. A has 6 pi electron. This A has 6 pi electrons, so it is aromatic. What about B? B also has 2 plus 2 plus 2, 6 pi electrons. It is also aromatic. What about this? Yeah, correct. Third one, you tell me. Third one. Is it anti-aromatic? Yes or no? Okay. So this one is non-aromatic. That is what, like, this is how you are making mistake. You make mistake in the exams. This nitrogen is sp3 hybridized. So sp3 hybridized won't take part in resonance, non-aromatic. Correct. What? Nitrogen is sp3, no? Fine. What about this pyridine? Pyridine? 8 pi. How many pi electrons? 6 pi. See, pyridine has 6 pi electron. I have discussed this many times in the class that this lone pair is not involved in resonance, and that is why this is pyrrole and this is pyridine. The basicity of pyridine is more than to that of pyrrole because this lone pair is involved in resonance, but this lone pair is not involved. It is available on the nitrogen atom. Correct. This 6 pi electrons aromatic. Okay, so must remember this basicity characteristics also and aromaticity also. Oxygen here with two lone pair, double bond, and here we have double bond O with two lone pair. One lone pair on nitrogen, double bond O. What? How it is? See, again you are making the same mistake. What I said, the number of lone pair present onto the atom, out of that, first of all, you have to judge how many lone pair are involved in resonance. You are considering all lone pair is involved in resonance. See, whenever nitrogen is bonded with single bond, right? Whenever nitrogen is bonded with single bond, then the lone pair present on nitrogen is involved in resonance. Right? That is in general it is true, but there are some different cases also. In this one, you see the number of pi electrons here. One lone pair of this oxygen, and here we have 2 and 2. So we have 6 pi electrons here. In this one, you see one lone pair, 2 plus 2, 6 pi electrons. One lone pair, 2 plus 2, 6 pi electrons. Again, one lone pair, 2 plus 2, 6 pi electrons here. This lone pair can go here, this will go here, and then again, when this comes here, the resonance is possible. See this, you just take care of one thing here. This bond, this pi bond is here with this bond. It is not with the nitrogen. So this is a single bond. So whenever the nitrogen is bonded with all single bond, then the lone pair of nitrogen is involved in resonance. Right? Here also you see 6, 6. Oxygen, only one lone pair is involved in resonance. Right? So all these electron molecules has 6 pi electrons and all are aromatic. Double bond O. See that this double bond O we don't count. We only see the compound, the aromaticity, the condition is what? Ring must, there must have, we must have cyclic ring. So when you only consider cyclic ring, because of this double bond, what happens? This carbon is not sp3 now. It is sp2. So that is the benefit of this double bond O we have. If this double bond O is not present, you write down OH here, single bond OH, then all these compounds are non-aromatic then. You understood? So the double bond outside the ring, that we don't consider. Okay, because of this double bond, this carbon becomes sp2 and then it is involved in resonance. That is the only benefit we have. Right. So you see this kind of questions, like they have given one question, like 7, 8 questions they have given, structure they have drawn in JE, and they have asked how many of these structures are aromatic. Okay, it is there in the previous year paper. You can go through. I don't have that question now, otherwise I would have given you. But we have discussed so many structures so far. Okay, on aromaticity. So if you keep all this structure in mind, if you revise all this, you can do those kind of questions easily. Okay, all those factors that we have discussed in this. So this is one type of question, whether you have to decide whether the compound is aromatic, non-aromatic, or anti-aromatic. Okay, sometimes they ask question like this also. This question you see. Concept is aromaticity only, but different types of question. Now suppose if I draw this structure, double bond here, you have to find out which nitrogen atom, which nitrogen atom will be protonated first. Means if H plus is there to attach with this nitrogen atom, where this H plus will attach, on this nitrogen or the another nitrogen. Suppose this is first, this is second. On which nitrogen atom the H plus will attach first? Reason why it is second? Yes, because the first is involved in resonance, unavailable for bonding, this lone pair. this lone pair is not involved in resonance. Another way what you can say, the same thing, another way what you can say, if H plus attach over here, right, then the aromaticity has been lost, right? So the compound will become comparatively unstable then. Okay, if H plus will attach here, aromaticity will be maintained and hence the compound will be still stable, right? And the second thing, which is the same thing, we have this nitrogen, this lone pair is involved in resonance, so electron density is less here. Tendency to take H plus will be lesser than this nitrogen, so the second nitrogen will be protonated first. Clear? This one, this kind of question is required in reactions actually, like which bond will break and how the bonds will break. There are two possibilities, right? Since chlorine is more electronegative, so this will take this bond pair of electron. One possibility is this, and it forms this product. Positive charge, double bond plus Cl minus. Another possibility is what if this bond is taken up by this carbon atom, then the possible structure will be this negative charge here, this one and this one plus will get Cl positive charge on it. Which one of these is possible and why? This is the first one and this is the second one. Which one of these is possible? Why first one? Purvik, Ritvik. Second one is correct, Sandarya. Why first one? Yeah, you see, when this bond breaks, right, this compound is highly stable because of aromaticity. This is aromatic compound. This is not aromatic, right? This is anti-aromatic, 4 pi electron. This is anti-aromatic. So, however, like you see, chlorine being more electronegative element, since aromaticity is here, then the chlorine will not take electron, but the carbon atom here will take electron and gains stability. So this is how the bond breaks. Okay, so you see the aromaticity will always be preferred, right? Whatever the condition we have. This is, yeah, it is unstable, but since it is aromatic compound, it is highly stable, so this will be favorable. Even here also chlorine will be little bit more stable than here, but this is highly unstable anti-aromatic compound. So we'll prefer this one. This one is right and this one is not possible. Okay. One more example you see. Here we have chlorine. Now how this bond break, either this carbon will have positive charge or negative charge. This carbon will have positive or negative charge. Yeah, if it is positive, this is not right. Then the ion is tropylium ion. With this positive charge on this, the ion we call it as tropylium ion, which is aromatic, right? So here this Cl will take this bond pair of electron and goes out as Cl minus, and here we'll have the positive charge because we are getting aromatic compound here. Okay, so that's the another type of see this kind of question you will require in reaction. Suppose you have to form some product and how the bond breaks. So aromaticity you have to also keep in mind. Okay, one more question you see. Double bond here. This compound has high dipole moment. Or dipole moment. So what is the reason of this dipole moment? See, the point here is what? Okay, you think on it and tell me first. Why Purvik? Why so? Yes, that's the reason. See, the reason of dipole moment is what? Charge separation. Okay. Actually, when you have some positive negative charge center, then because of this difference, we'll have the dipole moment, right? So in this molecule also, since the dipole moment is there, so we must have some movement of electrons, right? Because of that, the charge center will create, and because of that, we'll have dipole moment. So the point is this double bond here, right? If this double bond comes over here, then here we have the negative charge, the negative and pi electron, 4 pi electron, the compound is become then anti-aromatic, right? If this pi electron comes over here, so we have negative charge here and positive charge here. Because of this separation, negative and positive, this ring is also aromatic and this ring is also aromatic, right? So in this, the movement of electrons or pi electrons takes place like this. and because of that, the molecule becomes aromatic, and that is the reason of dipole moment, the separation of charge. Double bond here will have the positive charge, here we have negative charge, and this double bond will be as it is. Now you see this ring has 6 pi electrons aromatic, and this ring has 2 pi electrons again aromatic. So shifting of electrons takes place like this, leads towards aromaticity, highly stable, and this, because of this charge separation, the dipole moment is there. Is it clear? Okay, so this is it for aromaticity. Okay, we have done so many examples. Those examples you must remember, and then some reactions of aromatic compounds. We have benzene and all that is there in alkyl halide also, there in nitrines also, amines also. So those reactions you can revise, right? So those reactions, the mechanism based on aromaticity only. You must have remembered that ortho substituted product we get when the double bond breaks of the ring. So when the double bond breaks, so that will leads towards what, less stability, because the aromaticity is being lost over there. To gain aromaticity again, the H plus comes out, and again we'll get the double bond. So that all those reactions based on aromaticity only. All the molecules which is aromatic will not tend to lose its aromaticity, because aromatic compounds are the most stable form we have. Okay, yeah, we'll take a break, Ritvik, at 12:30. Okay, we'll take a break of half an hour, because I will also take lunch. Okay, so 12:30 we'll take a break, then we'll start at 1 o'clock. Will it be fine, or you want to take it the break now only? Okay, so we'll take a break at 12:30. Now we'll start this. We'll start this chemical bonding concept. Can we discuss now? And after the break, we will discuss that in all tautomerism thing. Okay. What we should is start in chemical bonding. Tell me, what is the doubt you have? Any specific topic? Because there are many things. I cannot start from the beginning. Okay. Any specific topic you can mention? Yeah, I'll start from there. Okay, MOT. VSEPR, you know all, right? Okay, hybridization and MOT. Okay, so we'll start with valence bond theory. Okay, that will, that will contains hybridization also, and then we'll move on to MOT, because if you have to discuss MOT, first you have to understand hybridization, and then magnetic behavior in all. Right. So we'll start with VBT, valence bond theory. VSEPR, you know all, right? Okay, from VSEPR onwards. So we'll start then VSEPR, then VBT, and then MOT. So we'll go a bit fast then, okay? See, valence shell electron pair repulsion theory, that is VSEPR. It actually deals with the shape of the molecule, shape, geometry, and bond angle. It's mainly with shape and bond angle. Okay, so write down the heading first. Vsepr, valence shell electron pair repulsion. As the name suggests, in the valence shell, whatever the electron pair we have, there we have some repulsion into that. Okay, it deals with the shape of the molecule. Okay, so there are some, a theory of this particular concept we have. So 3-4 points we have. You just write down quickly all those points. First point, the shape of the molecule. Shape of the molecule shape of the molecule is determined by the repulsion between the electron pair in valence shell. The order of repulsion is this. First of all, we have lone pair repulsion, right? Then we have lone pair, and then we have bond pair. Lone pair repulsion will be maximum, then lone pair, bond pair. Reason of this is lone pair of electron occupy more space around the nucleus, then we have more repulsion. Okay. Now to calculate, in this also we have one more thing. If you have multiple bond means double bond or triple bond has more number of electrons. So obviously multiple bond will produce more repulsion. Than single bond. These are some points we have of VSEPR. Okay. Now how to calculate the geometry and shape? To find out the geometry and shape, why I'm giving you this theory? Because on the basis of this theory only will do. So if you do not get this, you will not understand that. Okay, so just 2-3 points write down quickly. We'll calculate the total number of electron pairs. Number of electron pairs on central atom. On central atom. Second one, multiple bond here. Multiple bond will be treated as single bond. Third one, place the electron pair. Place the electron pair around the central atom. In such a way that they experience minimum repulsion. Okay. So now you see in this number of electron pair you have to find out first. Okay. and that number of valence electron. Like you see, suppose if I take one example, with the help of example only we'll discuss. When the number of electron pair is 2, then the shape will be linear. All these things, number of electron pair is 2, shape will be linear. Electron pair is 3, shape will be trigonal planar. Okay, just you write down this first. Next slide, let me write down this. Suppose the first case we have number of electron pair is 2. Now in this electron pair we can have bond pair also and lone pair also. Electron pair, whenever we say, we mean both bond pair and lone pair, right? So the possibility is what? Since electron pair is 2, so for any molecule we should have at least 2 bond pair. One bond pair is not possible for a molecule, right? So number of bond pair is 2, then lone pair will be 0, then only 2 plus 0 will be 2, right? So in this case the general form of the molecule will be AB2 type, right? And the geometry for this type of molecule will be linear, and this will be A, B, like this. Bond angle will be 180 degree, right? Example, we have BH2, CO2, etc. Okay, quickly I'll write down this few 4-5 examples. If you have electron pair 3, then in this one possibility is what? The first possibility is we have 3 bond pair and 0 lone pair. In this case, the type of the molecule will be AB3 type because we have 3 bond pair, and the geometry will be what? Or shape will be trigonal planar. Another possibility is what? We have 2 bond pair and 1 lone pair. The type of the molecule will be AB2 type because the lone pair, the number of bond pair is 2 only, so AB2 type molecule, right? In this case, the shape of the molecule will be bent shape or V shape or angular shape, anything you can say. So AB3 type molecule, if you see, it is like this: A, B, B and B, AB3 type. If you have one lone pair, then one B, you just remove this one B and you place a lone pair over here, right? This is what. So while we are talking about the shape of the molecule, this lone pair you don't have to consider. You just remove this lone pair and then you see it looks like V shape, right? Angular shape, bent shape or V shape. That's why the shape is V shape, angular shape or bent shape, right? So the point is, however, the geometry of this molecule is trigonal planar only. Trigonal planar. Geometry is trigonal planar. Here, the geometry and shape both are trigonal planar. So one thing you must keep in mind, here if you talk about the bond angle will be 120 degree. And since we have one lone pair, here we have bond pair repulsion. But here we have lone pair, bond pair, lone pair, bond pair, bond pair, bond pair repulsion. So because of this, the lone pair will suppress these two bond pair because the repulsion is high. So bond angle here is less than 120 degree. Is it clear? Right? So like this, there are many other possibilities. Electron pair when you have 4, right? Then we have bond pair 4, lone pair 0, bond pair 3, lone pair 1 bond pair 2 lone pair 2, like this. Okay, so like that we can form different compound, but the bottom line of all these stories, what, just one thing you have to keep in mind: whenever lone pair is 0, right, whenever lone pair is 0, then the shape and the geometry of the molecule will be same, right? Whenever lone pair is 0, then shape and geometry will be same. Whenever lone pair is present, then the geometry will be same. You see, for both the molecules, right? If I take one example here for bent shape, it is SO2, right? And for this AB3 type, suppose I'm taking SO3. So for both the molecules, the geometry is trigonal planar only, right? But the shape for this, since it contains one lone pair, it is bent, and for this trigonal planar. Why? Because there is no lone pair. Understood? So the point here is what? If electron pair is same for all the molecules, for the given molecules, if the molecules has same number of electron pair, then their geometry will be same, right? Shape will be different according to the number of lone pair present. Fine. Why it is different? Because the lone pair bond pair repulsion. Right. One more example I'll write down. Then we'll see some one more electron pair fold I'll write down. Then we'll see some examples directly. Suppose we have electron pair fold. So one possibility is what? That we can take bond pair 4 and lone pair 0. Another possibility is what? We can take bond pair 3 and lone pair 1. Another possibility is what? We can take bond pair 2 and lone pair 2. Possible, right? 3 lone pair and 1 bond pair is not possible. Okay. So in this case, you see, whenever you have 4 bond pair and 0 lone pair, so the geometry and shape will be tetrahedral. I am not writing down geometry and shape here. It is tetrahedral, geometry and shape. Both will be same since there is no lone pair. Now, when you're talking about the geometry of this, geometry will be tetrahedral only. Geometry will be tetrahedral only because the number of electron pair is same. For this also number of electron pair is same, so geometry will be tetrahedral. But the shape of these 3 molecules will be different. Okay, if 3 and 1 we have, then you see, if I write down the example here for 4 and 0, it is CH4. CH4 has tetrahedral geometry. And how do we write down this structure? Carbon, hydrogen, right? Hydrogen we have here, 3-dimensional structure I am drawing. Another hydrogen is here, and one more hydrogen is here. Bond angle is 109 degree 28 minute for tetrahedral. Now what happens if you want to draw this bond pair 4 and lone pair 3? Suppose I am taking the example for this is NH3. For this one it is NH3. For this one it is H2O. We know in H2O oxygen has 2 lone pair, NH3 nitrogen has 1 lone pair. So structure of NH3 will be what? Out of this one in place of 1 bond we'll have 1 lone pair, and then we have 3 hydrogen. I'm drawing it simply only. And then if you draw H2O, so H2O will be like this. And then here we have 1 lone pair, and here we have another lone pair. So if you compare the bond angle here, if it is θ1, so theta is less than θ1, and here this θ2, it is less than theta even. If it is theta here, and if it is θ2. Understood? Because we have lone pair, 2 lone pair, we have repulsion over there. The point here is what? For all these molecules, whether it is CH4, NH3 and H2O, number of electron pair is 4. So geometry will be tetrahedral only. But according to this lone pair, when this lone pair is present, now you see, if you try to understand this, see, whenever we try to find out the shape of the molecule, lone pair we don't consider in shape. So if you see the structure here, I'll just draw it in the next part, NH3. What is the shape of NH3 molecule? What is the shape of NH3 molecule? NH2O? NH3 and H2O. NH3 is pyramidal, and how it is pyramidal, you see, if I'm trying to draw the three-dimensional structure here. So this is the dotted line going away from you. Hydrogen, hydrogen, and hydrogen. So this bond, it is coming towards you actually, right? And this is the bond going away from you. So this plane, this is coming out of your screen, and this is going inside your screen. And here we have nitrogen. Here we have nitrogen. And this nitrogen is connected with all these hydrogen. So it is like it is coming towards you, going into the plane, and from center, this nitrogen on right side of your, and one lone pair is this present here just above the nitrogen atom. So when you see this molecule, we have a triangle, right? And nitrogen is above triangle, right? See, nitrogen in this triangle is not in the same plane. So when you imagine this, we have a triangle, and in the upper plane of this triangle, the nitrogen is present here, right? So this looks like a pyramidal, right? This looks like a pyramid, right? This is a pyramid with triangular base. That's why we are calling it as trigonal pyramidal, or simply pyramidal only. Trigonal pyramid, or pyramidal, we also call it as simply. Why trigonal? Because the base is a triangle, correct? H2O when you draw. So H2O, the structure is this with two lone pair. And this, while like I told you, that when we try to find out the shape of the molecule, we don't consider lone pair. So you imagine this lone pair is not at all present here. The shape is what? Bent shape. That's why the shape is bent. Now the point here is what? While we are judging the shape of the molecule, lone pair we don't consider. We only consider the bond pair, right? But geometry, if number of electron pair is same, geometry is same. Is it clear now? Okay. Now suppose we'll see like this, we have electron pair 5, electron pair 6 and 7. So this, you must have the notes of that. Okay, you can go through. Now suppose if I give you the structure that is H2SO4, or you just try to find out for SO4 2 minus sulfate ion. What is the geometry and shape of it? SO4 2 minus, geometry and shape. See, there are two methods of it. One thing, if you know the structure, you can draw the structure simply. Now the structure of this will be what? S double bond O, double bond O, and O minus, O minus. Right? Okay. Do we have any lone pair present on this sulfur? We do not have any lone pair present on the sulfur. Right? Lewis structure, if you draw, you will understand that. Now the theory that I have given you in the beginning, how to determine the geometry and shape. The second point I gave you, you can go through that. A multiple bond is treated as a single bond. So if I ask you how many bond pair present in the molecule, what is your answer? How many bond pair? How many bond pair in this? Tell me how many bond pair present. Yes, the number of bond pair is 4. Why it is 4? Because this any multiple bond will consider this as a single bond only. So 1, 2, 3, 4. 4 bond pair, right? So there is no lone pair, only 4 bond pair, right? So its geometry will be what? Tetrahedral, and shape will be tetrahedral. Geometry and shape will be tetrahedral since there is no lone pair present. So like this, if you know the structure, you can easily find out the number of bond pair. Only thing you have to keep in mind, we don't count this as 2 bond pair, it is 1 bond pair of electron. Any multiple bond we consider as 1 bond pair. The another way, because structure is difficult to memorize, the another and easier way to find out the geometry and shape of any molecule is to find out the number of valence electron. Suppose it is n, right? Now what we do, this n should be divided by 8. You will get some quotient here, right? And then you will get some remainder. This quotient gives you the number of bond pair. This remainder gives you the number of electrons in the lone pair. To take care of this thing, R is the number of electrons in the lone pair. So number of lone pair, if I have to find out, number of lone pair will be R by 2. Is it clear? So electron pair is what? Electron pair is Q plus R by 2. This is the number of electron pair. Now for this one, if I apply this rule here, for SO4 2 minus, sulfur has 6 valence electron, oxygen has 6 valence electron, 6 into 4 plus 2 negative charge, so 2 for that. So it is 32. Now this 32 will divide by 8, so it gives 4, 32 and 0. So we have 4 bond pair and 0 lone pair. So number of electron pair is 4, and when the number of electron pair is 4, geometry and shape is tetrahedral. Understood? So this by 8 method will find out. In hybridization also will do the same thing. Try to find out the shape and geometry of this molecule. IO3 F2 minus. What is the shape and geometry of this? What is the shape and geometry of XeO2? XeF4? ICl3? H2O? CH4? NH3? Tell me. Okay, what is the answer? Tell me. Trigonal bipyramidal. What is the number of valence electron here? For iodine it is 7. So 7 into 3, because 2 fluorine we have, 7 into 3 plus 6 into 3 plus 1 negative charge. So 1 for that, it is 40. So 40 divided by 8 gives you 5 bond pair and 0 lone pair. So this is what trigonal bipyramidal is, geometry and shape both. Because the lone pair is 0, geometry and shape will be same. Trigonal bipyramidal. XeO2, number of valence electron 8 plus 6 into 2, that is 24. So 24 divided by 8 gives you 3 bond pair and 0 lone pair. So this will be, oh, it is 20, no, 6 into 2 is 12, 12, okay, it's 20. So 20 divided by 20 divided by 8, so it is 2 bond pair and 2 lone pair. Right? 2 bond pair and 2 lone pair. Electron pair is 4. So geometry will be what? Tetrahedral, since 4 electron pair we have. But shape will be what? Bent shape or V shape. I'll tell you hybridization also. Wait. I'll tell you hybridization. Let me finish this first. XeF4, 8 plus 7 into 4, 36. So 36 by 8 gives you 4 bond pair and 2 lone pair. Right? So 4 bond pair and 2 lone pair, the geometry will be what? Octahedral. And shape will be square planar. Like this you can do this. Okay. H2O. If hydrogen is the outer atom, what is the valence electron we have here? 6 plus 2, 8. When hydrogen is the outer atom, the last 3 cases, will divide this 8 by 2, not by 8. Right? So here I am taking 8 here in all these compounds. When hydrogen is the outer atom, so we'll take 2, not 8 here, because hydrogen can have maximum 2 electrons. So it has 4 bond pair and 0 lone pair. Geometry and shape will be tetrahedral. Sorry, it is H2O, no? Right. So we have only one mistake. See, we are getting 4 here, right? But you see, there are only 2 hydrogen atom present. So we can say out of 4, here we have 4. So out of 4, we have 2 bond pair and 2 lone pair. So uh, geometry will be tetrahedral and shape will be bent. For CH4, you see, carbon it is 4, hydrogen 4. So 8 by 2. So we have 4 bond pair and 0 lone pair. Geometry and shape will be tetrahedral. Similarly, for this one it is geometry will be tetrahedral and shape will be pyramidal or trigonal pyramidal. Okay, this one we have already discussed. Okay, now this bond pair and lone pair, the sum of this bond pair and lone pair, we also call it as steric number, which is nothing but the electron pair is nothing but the steric number. Now, when steric number is 2, right, hybridization will be sp. Steric number and hybridization. If it is 2, hybridization is sp, 3 sp2, 4 sp3, right? If it is 5, then sp3d, 6, then sp3d2, like this. Okay. If it is 4, then dsp2 is also possible, which is there in coordination compound. This hybridization will get in coordination compound when inner d orbital is involved. Okay. So when you have this number, that is electron pair or steric number will be same. That will be the sum of number of bond pair and lone pair. So if it is 5, then its hybridization will be sp3d in case of 5. Like here you see it is 4, so hybridization for this is sp3. If it is 6, then hybridization is sp3d3. D2, sorry. If 7, then it is D3. If here it is 4 again, so hybridization is sp3 for all these molecules. Is it clear? So we'll just, the molecule, given molecule, will divide it by 8. We'll find out the number of bond pair and lone pair. The sum of that will be the steric number. If steric number is 2, hybridization sp, 3 sp2, 4 sp3 or dsp2, 5 sp3d, 6 sp3d2, 7 sp3d3. That is it. Like this, we find out the hybridization. Understood this? What? Okay. One more point in this, the last one. Write down hybrid orbital. Hybrid orbital never forms pi bond. See, there we can understand this also. There are, explanation of all this that we can also discuss, but we don't have that much time. And the last time January you are going to write down JEE main exam, so there's no point going into those details. Okay, just these points you keep in mind. Hybrid orbital never forms pi bond. So if you have any organic compound, suppose it is given. Okay, all these compounds like this, suppose there are compounds given. So in this, if you have to find out the hybridization of each carbon atom, this all these carbon atom, this nitrogen, these two carbon atom. Okay, so in this kind of question, since we cannot find out the number of valence electron and then all those things, so when the structure is given like this in organic chemistry, then you just count the number of sigma bond. Number of sigma bond. If number of sigma bond is 3, sp2, number of sigma bond is 2, sp, number of sigma bond is 4, then sp3. These are the only three general things you'll get in this kind of question. So for this carbon, what is the hybridization here? Number of sigma bond is C double bond OOH. So one sigma with double bond, one here, one here. We have three sigma bond. So this carbon is sp2 hybridized. We only count the number of sigma bond. This carbon atom, we have 4 sigma bond, sp3. This carbon atom, we have 4 sigma bond, sp3. All these carbon atoms in the ring are sp2 hybridized because we have 1 sigma bond. sp2, sp2, this is also sp2, this is also sp2, sp2 and sp2. This carbon atom, again sp2, 1 pi bond. This carbon atom, sp2. Right? What about this nitrogen? This nitrogen has 1, 2, 3 sigma bond and 1 lone pair. So it is sp3. Understood this? Okay. So this kind of question you will get in hybridization. Okay, and then you can solve this. Any doubt you tell me, otherwise we'll take a break now. I'm tired. Okay. Okay. Take your lunch then. Yeah, Ritvik, in hybridization we count lone pair also. That's why you see NH3. You see NH3, for NH3, what is the steric number? We have 3 bond pair and 1 lone pair. Steric number is 4, sp3. So 1 lone pair we are counting here. Then only it is 4. Okay? Okay, chalo, we'll take a break. We'll start at 120.